This is just one example from Transpower, where about 28% of total generation is from wind by 2050, and that would require between 1 and 2 wind farms to be built every year. So looking at the overall expected changes in wind speeds in New Zealand by the end of century, we can see that here that the average wind speeds are going to decrease in the North Island and increase in the South Island, and this just becomes more pronounced under the higher RCP scenario, which is the high range emission scenario. For strong wind speeds, so like the 99th percentile, it's a similar pattern of a decrease in the North Island and an increase in the South Island, except in the high altitude areas of the South Island, where we see a bit of a decrease. However, the changes in wind speed don't directly relate to power output changes, and wind speed and wind power do not have a linear relationship. So increasing wind speeds don't necessarily relate to more wind power. The cut-in wind speed is the minimum wind speed that a turbine can extract power, and that's around 3 meters per second. And the cut-out wind speed is the maximum wind speed that a turbine can generate power, which is around 25 meters per second. And after this, it just has to turn away and be protected from strong winds. So due to the cut-in and cut-out wind speeds, like understanding the changes to extreme wind speeds is a crucial part of the study. And the study examined changes to wind power output at 2 existing New Zealand wind farms by mid-century under climate change. Moving on to the methods, wind speed data for the past 10 years was obtained under a confidentiality agreement from Meridian Energy for 2 wind farms, Uku and White Hill. Uku is up in the Waikato area and White Hill is in Southland. We also got turbine power curves for the specific wind farms from Meridian under the confidentiality agreement we had with them. And wind speed projections were obtained from NIWA for the nearest climate stations at Hamilton and Lumsden, and they were projected from 2025 to 2065. Gosh, give me a sec. Just gonna, there we go. So we looked at 2 emission scenarios, RCP 4.5, which is the mid-range emission scenario, and RCP 8.5 for high emissions. The wind speed projections were for 6 different downscaled global climate models, but the projections we received were for 10-meter wind speed height, and we wanted to look at the 80-meter wind speed height, so we used this conversion up here. Kind of as you'd expect, the higher elevation wind speeds had more incidences of high wind speeds, but this allowed us to better understand the extremes. So to obtain wind speed projections for our specific sites, we determined the linear change in projected wind speeds for different percentiles over time for each global climate model and RCP scenario at the climate station locations. And then we applied this change to the wind farm observed wind speeds to synthesize wind speed data for each percentile, which gave us the hourly projections. And we wanted to look at 10-minute data to just, again, look at the extremes a bit more closely. So we just synthesized those, and finally, we put all this data through a power curve to determine the future power output. So what did we find? First, we found that the wind farms, which are the blue lines on the histogram, showed like a more high wind speeds than the climate station sites, which is what we expected, but it's just to justify why we synthesized projections for the specific sites rather than using climate station data directly to find the changes. We also found that there's quite a lot of uncertainty in how wind speeds will change under different global climate models. So these graphs here, the red line is the observed mean wind speed, and the histograms show the spread of the mean wind speed for each of the 6 global climate models. And we've got RCP 4.5, the mid-range emission scenario in blue, and RCP 8.5 in orange. Overall, the models predict increases in wind speeds over the 40-year period, but there's quite a large spread in model projections. Uncertainty between higher projections is higher under the uncertainty between global climate model projections is higher under RCP 8.5. We also looked into the time spent above and below the cut-in and cut-out wind speeds, and we found that the time spent below the cut-in speed is expected to reduce, so we'll get faster wind speeds at the lower end of the spectrum, and the time spent above the cut-out speed is expected to reduce under RCP 4.5 and increase under RCP 8.5. So moving on to the actual projected power output, we found that changes over time are non-linear for different wind speeds, and there was an increase in the number of periods that had power output at the top end of the scale, so up at 2,000 or 2,300 kilowatts. And there was also a decrease in periods that had no power. So at the top end of the spectrum, we've kind of got higher wind speeds, and at the bottom end of the spectrum, again, we've got higher wind speeds. Between the extremes, it's kind of hard to say what's going on there, or we can't find anything definitive. So looking at the power output changes over time, we found that both wind farms are projected to increase their total power output from current turbines in the coming decades. We might expect higher emissions to result in higher wind speeds, and at White Hill, that's the case, but at Te Uku, where higher emissions resulted in a smaller increase than the moderate emission scenario, but still an increase. So looking at the graph here, you can see that power output is expected to increase by between 1 and 3.5%. But what this actually means, without telling you all the information, the actual power output under the confidentiality agreement is at so for White Hill under RCP 8.5, where wind speeds, the power output is expected to increase by around 3.5%. This is equivalent to 6.3 gigawatt hours a year, and so which is around the equivalent of the power output of just one turbine in a year. And wind turbines cost a lot of money, so this, may help with planning in the future or saving some money, hopefully. So what I hope you take away from my presentation today is that wind speeds and power output are going to change in the future, and these changes need to be investigated in a spatially and temporally granular way to account for the non-linear changes anticipated across the wind speed distribution. The projected changes to power output at the 2 wind farms aren't large, and the uncertainty between different models under different emission scenarios is high. However, the mean changes across these is important. At White Hill under RCP 8.5, power output is expected to increase by 3.5%, which, as I just mentioned, is about the equivalent to the power output of one turbine. And at the recently constructed Harapaki and Waipipi wind farms, turbines cost between $7 to $11 million each. So this could be quite significant. And knowledge of these future projected changes could be incorporated into the planning of new wind farms.
Thanks, Francesca. Awesome. Yeah. I think we've got time for one quick question, if anyone's got a question. Nice.
Just wondering whether the models are accounting for changes in turbulence and hence gustiness and atmospheric stability.
Well, actually,
what impact
all of the models are kind of accredited to focusing on different wind forces differently. And so some focus on like El Nino and the future climate effects of that, or El Nino, and others focus more on the temperature gradient. So I can't tell you the specifics, but the models all focus on slightly different climate forcings a bit more, and because they're international global climate models, so each station kind of has their focus on what they think is going to be the most predominantly affected in the future, which makes quite a big difference.